Okay, so if you don't mind, I'm gonna start uh, so we can go on and we don't really take too much of your time. So welcome everyone. Today we have Johannes Hulsman from University of Geneva, and he's going to be presenting this very interesting topic on lunar energetic particle environment detector called LUMPAN, I believe. Thank you very much for accepting to give this talk, and we are listening to you. Thanks.
Thank you for inviting me to give you this talk. Um, as was just briefly summarized, I'll be introducing the Lunpan experiment, which is a compact detector for deep space particle detection, which I will address further down the road. But in this case, it's an evolution of something that we've been working on since almost 10 years now here at the university. And now targeted, of course, for lunar applications. So let me cover this. So to give you a brief overview what Lunpan is about, it is a orbital mission meant for 3 years around the moon, with the intention of mapping the particle environment of high energy charged particles, gammas, and neutrons. So we were selected by ESA's call for a small mission for exploration destination to the moon. We actually completed that last year. So what you will see today is basically the findings from that study. And early this year, we got an answer from ESA about the next stage, which I will explain. Well, I'll summarize to you where we are at the end of today's talk. Now, the main fields to which Lumpan is going to contribute are physics in GCR, solar energetic particles, and lunar geology, with secondary sciences being space weather, radiation dosimetry for human spaceflight, and of course, technology development for future and different missions. Now, if we look specifically at galactic cosmic rays in deep space, we know that galactic cosmic rays are powerful cosmic messengers. They are likely produced through violent astrophysical events, but carry actually trace information on dark matter and antimatter. We have actually studied them intensely in the low energy region as well as in the very high energy region. But as you can see in the figure here, there is this MEV gap. The problem being here that the past missions that we have, the balloons as well as the orbital missions that are orbiting the Earth, they are impacted by the magnetic field. So as a result, you can only see the very high energetic particles that are passing through. Now, if you go into deep space, we don't have too many experiments that have gone there. And as a result, you are much more impacted by the high flux of low energy particles. So you get this sweet spot, which is this MEV, this GeV range, which is not well mapped. And this in particular is also the point where a lot of constraints can be derived. So this is the part where we, with Lumpan, want to actually address. So we know that if you study this GeV range, you can study the acceleration mechanisms of these galactic cosmic rays at their origin, as well as use that information to constrain and available and applicable models regarding propagation through the interstellar medium. So this is the science case regarding the galactic cosmic rays. Now, when we look at solar energetic particles, we know that solar energetic particles are quite complex, since they are basically a superposition of different mechanisms. So they're very difficult to disentangle. Then, of course, we know that they depend on the solar activity itself being more or less frequent. And then again, we have this interaction or this interplay with Earth's magnetic field. Therefore, if you go further away from Earth, so in deep space, sorry, suddenly got a call.
It's,
Um, so we know that if we go into deep space, do you see my slides? Yes.
yeah, we do. Yeah.
Yeah. So we know if we go into deep space, we will be able to address solar energetic particle flux profiles more appropriately. However, past experiments are actually limited by the lower part of the energy spectrum. As you can see here, it is significantly more dominant. And then at some point, the GCR spectrum starts to take over, which is what you see on the high energy part. So right now, the predominant models are really emphasized on every bits of information that they have in this energy range. So we know that by having constraints from particles in the GeV range would actually uh, uh, provide new insight to their models that they have. In addition, we know that if you look at the SCP particle acceleration mechanisms, you can actually constrain this further on with GeV data. And finally, when it comes to this is more of a secondary science, but it is rather important for ESA missions. If you look at human spaceflight and human dosimetry models, having this piece of information is actually quite critical because these GeV particles are penetrating, so you cannot really properly shield against them. Therefore, you need to model them properly to actually prepare in advance regarding any form of space mission, space flight to the moon, what needs to be done. Now, the third major science case are lunar albedo particles. Now, as I said, we have GCR particles, but if they are striking the lunar surface, they actually generate secondary albedo particles. These are neutrons, gammas, electrons, and protons, and among many others. Now, the spectrum that you expect to see is something as shown on the top right. So this is something a student in our group developed. So if you assume the GCR impinging the surface, you would get at 100 kilometers from the lunar surface this particular spectrum. And of course, as you go further away, this spectrum decreases by r squared, but in particular with neutrons, since you're also moving further away, you have the decay time that you need to account. So at some point, it drops off. So this is important when you think about a particular mission because these particles are not only just a nuisance, but they actually are useful to understand the lunar geology in general. For example, neutrons can be used to probe the hydrogen content and as a result, the content of water that you have on the lunar surface. Of course, up to a certain depth only. Now, there was a past mission which mapped the lunar flux. So this was a dedicated neutron detector on board the Lunar Reconnaissance Orbiter. So this is this Lunar Exploration Neutron Detector. But what we try to do is we want to do a long-term monitoring to actually see the overall structure. So even though it is not competitive to this lunar exploration neutron detector, it is complementary to the field in general, since it's a long-term monitoring device. Uh, Finally, together with the information that we would get with the GCR and solar energetic particles, we can actually extract much more of what is going on the lunar surface. But this brings us to the technical part of it. I mean, the science is nice, but how do we achieve it? Now, the problem with high energy particles is that they are by nature very penetrating. So the only way, I mean, not the only way, one of the ways of stopping them would be actually just brute force, which is this DEE methods. But the problem with that is that you would need a huge amount of material to actually block these high energetic particles. So if you look at this particular figure, The way to actually extract the particle energy would be then you have stacked layers of, let's say, silicon or any particular material that are sensitive to the particle to create a signal, uh, but also with a high Z to allow them to lose the energy. But the problem with that is that if you want to do it in this GeV range, you would need, for example, for one GeV protons, 170 centimeters of silicon. Now, this is, of course, a problem because we cannot send nearly 2 meters of silicon to do this kind of exercise, let alone having even something in between them. So this is a no-go scenario. And that's another problem that you have with this methodology is that this produces a lot of secondary. So if you want to do particle identification, you need something that is a bit more elegant than this approach. And the final problem that you have with this DE E method is that trying to stop the particles cannot be done at very high rates. So how do we do that? For these solar energetic particles, you get a huge flux of particles that come in a very short amount of time. So this is not even an option. On the lunar surface, yeah, you can have different conversations, but in space, where sending a mission is all about saving power, saving weight, saving data rate, all of these constraints, require you to come with a very innovative approach. And this is where PAN, this particle analyzer, comes into play. So I don't, you see this slide?
We are seeing this challenge of measuring high energy particles.
Yeah, but you don't see an orange box. Ah, okay, sorry.
Now we see.
Yeah, now it appears. So yes, so this is where PAN comes in. Now, the thing is, PAN is a magnetic spectrometer. It follows the heritage of instruments such as AMS, which are very famous in the field of charged particle measurements. But the concept of a magnetic spectrometer is very simple. You need a magnetic field and you need to have tracking layers, as you see here at the bottom right. But the problem there being is weight and channel count, which then translates into power consumption. So now you're going back into this circle of how can we do something at high rate but low power? How can we do something with high resolution but low weight? How can you're going back into the circle. So this is basically where LoonPan comes in. So we have three types of payloads, but two main. We have the PIXPAN instrument, which is a compact magnetic spectrometer, and we have a new PIX detector meant to look at the neutrons and the gammas. Now, I will describe each one of them a bit later, but the PIXPAN instrument is inherited from the Minipan detector that we built actually a few years ago. So we have this one sitting in the lab. We started with this initial concept of saying we need something small, we need something light, and we need something that can do tracking. Now, if you want to do tracking, you need a magnetic field. This is what you see here. You need tracker layers. This is what you see here. And you need something to say, is the particle going from one side or the other side? This is where the time of flight comes in. Now, since the magnetic field is only in one direction, you need a very high position resolution in one axis, and the other axis you don't care too much. This is why you have this strip X and a strip Y. Now, these are 90 degrees rotated to each other. Now, one of them is about 25 micron with strips of 25 micron, whereas the other one is, I think it was about a few hundred micron. I think it was 600 micron, give or take. Now, the thing is that the second axis is bad, of course, for position resolution, but you don't care too much because what you care about is the angle of the incoming particle. You need to know what the angle is of the particle when it passes through the first layer, when it passes through the second one, when it passes through the third one. And by knowing that and knowing, of course, what the magnetic field is, you can actually then do a track reconstruction. And by knowing the time of flight with this TOF detector, you know when it came, from which side it came. Did it come from the front or did it come from the back? Finally, we had these pixel detectors, and these detectors were at that point designed to actually produce information regarding the high rate phenomenology. Because this design, as you see here from Minipan, is very good for position resolution, but at kilohertz rate. Whereas the pixel detectors, they can go up to megahertz. So this is good for solar flares scenarios, but for galactic cosmic rays, where the rate is significantly lower, the other scenario is preferred. Of course, this was our initial design. We built it. This is basically what you see here. These are all the things we did for Minipan. We were designing the magnet from scratch. We did all the tests necessary regarding integration, the field tests that you see here. Then, of course, we designed the boards. So this is the strip X. So I was wrong. It was not 600, but 400 micrometer. So you see we have the two different strip detectors. They look very similar, but if you visually, hold them in front of you, you can actually see a distinction between them. Then integrated together, it looks like this as the prototype. And then the final result before going to a beam test, of course, looks like you see here on the bottom right-hand side. Now, this worked. Uh, this is what you see here. We found a position resolution of up to 5 micrometer and even less, well, dependent, of course, on the angle that we were operating, but up to 5 micrometer. Um, and we were able to distinguish particles up to Z22. So it was working, the concept was working very well. But we learned a few things from our efforts on this instrument, which is the whole motivation of PIXPAN, is that it is difficult to create a system with so many subdetectors. I mean, AMS is very famous. AMS has so many different types of instruments all working together, but it's also a big instrument on top of the space station. If you want to do something compact, you need to have something much more simplified. And this is why we said, okay, well, we need something more simplified than the time of flight system. We need something more simplified for the backend electronics, and we need something that is unified. Because if I talk about TOF being an own system, the tracker being an independent system, and a pixel being an independent system, I have 3 readouts. And somehow these 3 readouts need to communicate and talk to each other. So technically speaking, this is a difficult task to execute. And then you're asking again to the platform people like, I need more power because I have a computer that needs to do the analysis on board. So this is technically it's not a best choice. So this is where PIXPAN comes in. We said, well, I mean, we are with CERN. We have seen the good efforts with the Minipix group, and let's use a different kind of technology. And this is where TimePix comes into play. I'm not sure if you're familiar with this technology, but just to briefly summarize it, TimePix is a hybrid pixel detector, so it's really a very compact pixelated sensor that is generally about 300 to 500 micron thick. You can do whatever you want with a pitch of 55 micron, and it operates without a trigger. So it is always operating in a data-driven mode. So if you have a charged particle going through it, it passes a threshold, and this threshold immediately writes the file. So you can consider this as a trigger, quote unquote, but there's no additional logic, as you will, that is checking what is happening in particular. And then later on, it's just on a pixel by pixel basis, you have this threshold condition, and that's it. And then it will just tell you what the exact time was that you received it, what pixel it was, and what the charge was. And this is very powerful information because if you then do clustering, you can actually infer what kind of particle type you have, which allows us to actually use it for tracking information. Now, the good thing about this TimePix sensor is that it's dedicated for timing performance as well. So at LHCb, they're actually doing this analysis of using Timex4 for device under testing concept, and but standalone as a sensor, this technology can provide you already 200 picosecond timestamps just on a single pixel. So if you just have a hit and then again another hit, this can happen within 200 picoseconds perfectly. So you can see if I have a tracker that is about 30 centimeters or 20 centimeters long, and I want to know, is it going from one side to another side? I just need to do a very simple condition. Where did it arrive first? And this will fit in with this within this 200 picosecond. The second thing is that I don't need to do any complicated analysis regarding the amount of energy that was lost. I mean, I can just follow the position and then actually just do the tracking by itself. And the last good thing is that since it's a high rate device, I can automatically use this at megahertz levels, even though the standard rate is of course kilohertz, but this is the capability of the technology. Now this is very good. I mean, now I'm saying we're using one particular technology for everything. And that means from a readout perspective, it becomes significantly more simplified. So this is basically our whole concept that we have. We say, okay, we keep the same mechanical and magnets and everything because we know it works, but we just replace the trackers. So we know that the magnets are 0.8 kilos. We know that the whole instrument will be about 10 kilos, fitting inside a cube of about 20 times 20 times 20 centimeters, even though it's smaller inside, with a power consumption of 30 watts. And then that's it. It's one technology, one readout, small device, can do GeV range particle detection. Now we did see some simulations, of course, to test this with different sensor thicknesses. And this is what you see exactly here on this plot. So we did electron and proton energy resolution studies, assuming it would go through all tracks. And you can see that we can achieve with this particular design a energy resolution of less than 30%. If you look at deep space applications, you will see numbers that are often exceeding this particular number, exceeding 50%, and that's considered good. So of course, if you do LHC physics, then this is of course terrible, but in space, this is considered very good. So we are actually, quite happy to see that this design works. Now, since I'm trying to explain to you, the concept of the design itself, I'm very briefly going to show the schematic of how the instrument looks like. And you can see it's a very repetitive kind of design that we're just repeating and then connecting. And this is from a space mission very desirable, because if you design a space mission, you have a lot of points of failures. So if you design something that is repetitive, then you can easily flag a mistake and then repair or discard it and then just create a new one out of it. So this is what you see here. Very simple sensor with 3 buses that has data connector, power supply, and then of course a high voltage power bias, and that's it. And then it goes to the main platform, which then has a simple algorithm to figure out whether this is a background particle or not. So this is basically what I want to show on this figure, because as I said, we need to do some onboard processing. The issue with Timex sensor and ESA and as well as NASA, they know this very well, is that since they don't have a particular trigger, they produce a huge amount of data. So let's say you have one pixel that has a problem, recall that it can produce a new hit in 200 picoseconds. So if I have a faulty pixel, for example, and I do nothing with it, it will dump at the rate of megahertz, just data like that, unchecked. So you need an onboard selection algorithm as well as a monitoring tool to say what is going on before transmitting it to Earth. Now we have a very simple algorithm for that. The concept is quite straightforward. I'm saying if I pass through the first tracker and then through the second tracker, it is considered as mode 1. I will see much less energetic particles. If it passes through the first segment and the second one, as you see here, then it's considered as mode 2. So this is very basic, and the rest of the data is just a time coincidence, and the rest of the data is just dumped to Earth. And then on grounds, we then perform, the clustering algorithm, the application with sort of the correction with the calibration, the alignment, all of this to actually make sense of what it means. Now, if you look at the data rate, the benchmark that you would expect of pure raw data from the GCR is about 30 kilobytes per second. This is because the moon is casting a shadow, so it's blocking about, or well, not about, but almost half the spectrum. And then when you are further away, the moon is casting less of a shadow, and then you're approaching 40 kilobytes per second. And as you are applying a more strict cut, you can see that we're drastically dropping in rate. Now, when you do this with the albedo, of course, you actually are approaching, and then you actually expect to see about 6 kilobytes per second, the majority of which are well, in this case, yes, peak span, the majority of which are just charged particles. Now, peak span, as I said, is focused on the high energy part of in the GeV range. NewPix is actually designed to look into the lower energetic parts, since it's a single layer. So if I go back to this particular figure, as I would like to show, you'll see that I marked this into two colors. So this darker blue part is the part that PixSpan will address, whereas this part is the part produced by NewPix. And together we actually then have a huge energy range. Now, NewPix is using the same sensor technology as before. As I said, it has two neutron units and two gamma units, each one dedicated for a different for neutrons and gammas, of course. And both of them are facing in opposite directions, one towards deep space, one towards the surface of the moon. And you can see that the design is basically time peak sensor with silicon with a converter layer, and then again a silicon sensor and a time peak. So it's just a sandwich of multiple layers. Whereas with the NewPix unit, we only use the cadmium telluride as a material before the sensor itself. Now, focusing on the neutron units, as I said, we have a sandwich of multiple layers, and the converter layers are shown on the right-hand side here. So this is a 2D profile. I'm not sure if it's very straightforward, but let's start with the pure silicon layer. This is the baseline start. Then you put on half of it, which is this part, a polyethylene layer. Then on this part, you do another cross, which is a polyethylene and aluminum. So you have here pure silicon. Here you add polyethylene. Here you add aluminum, meaning that on this side, you actually have the silicon underneath plus this polyethylene and aluminum. Then finally, on the last square, you have this lithium-6. Now, why do we do this? The problem with NewPix, or it's not a problem, but the feature about NewPix is that in this hundreds kV range, it cannot say on a particle by particle level, this is where it comes from. So even though it is pointing toward the moon, it cannot say this came from the moon. It can only say, I saw this. So the way to do it is you have to do it statistically. So you have to expose yourself to a huge amount of particles. And by exposing yourself to a huge amount of particles, you will actually see different structures appearing on the sensor level. Because if you have the lithium-6, as it interacts, for example, with a neutron, you get an alpha particle, which you can actually recognize. This is, let's say, the magic of the neutron detector, these three concepts. So if you look at the free silicon sector, you will only see charged particles, right? Or you'll see a bias of charged particles. If you look at the lithium-6 part, you'll see a lot of additional alphas appearing because there's the impact of the neutrons coming in. So now if you subtract this spectrum from that, you get to see only what is the neutrons. This is a trick. So you say I have spectrum A, spectrum B, spectrum C. You subtract things from each other, and then you get to see the pure final spectrum from each particle type. Now, the way we do this is because the pixels are 55 micron thick, is you can actually extract it by looking at the cluster structure of each particle type. So an alpha particle, since it's quite big, it creates a huge structure. It's heavy ionizing, so you expect to see something like this as you see there. If it's a dot, it's something like an electron or an X-ray or gamma ray appearing. So each structure tells you something of what kind of particle it is. Now, this concept is not unproven. It is tested with Timex-3 technology. So with the predecessor that has been around for I don't know how long, like almost 10 years before. So the colleagues in Prague, they took the sensor to Los Alamos and they tested with a americium beryllium and a californium source. You can see the sources here. Sorry, the source spectrum here. And you can see the difference. If you just expose the californium source purely, you don't see much. But then if you look at the cluster structure, so this is just purely hit, nothing more. If you then start to apply cuts such as the size of the cluster, the energy of the cluster, then you get to see a particular structure. And you can see by subtracting these two from each other, you get to see something as you see on the top side here. This is a good example. Now, the converter that I showed here, this part applied here is visible again. Again, if you just expose it to the ambi source, you get to first see this, but then by looking at the energy levels, you can actually distinguish them more from each other. And this is the way we actually extract neutron information. Now, this is a bit more technical if you want to, whoops, sorry, if you want to understand the way it is done. But this is basically showing the efficiency, the detection efficiency of each part compared to with respect to the neutron energy. So you can see that in the EeV range, lithium-6 is preferred, at which point then it suddenly drops, which is why we are using this polyethylene instead for high energy neutrons. So this is a paper from the colleagues in Prague from 2 years ago. They are the main responsible for this particular payload. Then we have the gamma unit. The gamma unit is much more simplified. This is basically, we said, okay, we put a cadmium telluride sensor. So this allows us to measure the gamma ray flux in the 10 keV to 10 MeV range at a high rate. Nothing special in addition to what was done before. This was already proven with the Timex-3 detector, which is basically what you see here. So if you want this, you will probably have to contact them. I can email you. But this is basically the second type of the detector that we will be using. Now, in terms of design, as I said, it's very similar to what you saw with PIXPAN, since we're using the same technology. Very similar readout boards will be used with very similar readouts. The only difference being that there's no algorithm that does anything regarding event selection. So what is done with NewPix is that you have three different modes. You have the raw mode, which just vomits all the raw data like that. But this is a problem for data volume, which is why you have something called list mode. So this is an intermediate mode that collects all clusters and only sends, let's say, the high level data of these clusters back to Earth. So you have some onboard clustering algorithm is embedded inside the readout that says, well, I saw this cluster. This cluster has, I don't know, energy of 100 keV. That's what you transmit to Earth. I saw something with 100 keV. The rest of the information is lost. Then finally, you have the histogram mode, which is sending a compressed version of everything that you saw. So it's basically saying, I analyze, I extract the information, now I put it in a histogram, and that is what you send to Earth. And the reason why NewPix is forced to do that is because it has significantly more pixels compared to PixSpan. And of course, since that is the case, you have to do data compression in this way. There's no other way around it. Now, their data rate is expected to be as shown on in the table as you see here. As you approach the Earth, the Moon, you expect to see less GCR but significantly more albedo particles. So you expect to see about 30 kilobytes per second from the neutron detector, as well as 12 from the gamma detector. Then, of course, when you go further away, this drops, and then you see the GCR more. Now that we have these instruments described, of course, we go back to the mission. Now it comes more, realistic, and this is where, with our colleagues in Italy, we were then discussing, okay, what is the best orbit? Now, my requirement as a physicist was get me as close as possible to the surface, and then of course they look at me saying, please come with a more realistic request, and I say, okay, even closer, and then the Italians were not happy for. I think it took them a month for me to explain it properly, but the gist of it is very, very straightforward. Is that you have to make a balance between station keeping and science requirements. We physicists, we request whatever we want, and then the engineers, they look at us, and then they'd rather kill us because we're coming with ridiculous demands. So the initial case that we had was to have a near rectilinear heliospheric orbit. This was our very, very first, like 3 years ago, when we pitched the idea to ESA. And ESA said, but yeah, guys, I mean, it's good for station keeping, but your science case is severely compromised. So then, of course, we reversed it. We said science first, because this is of course our desire. And then we found that if you select an orbit at 100, orbit within 1,000 kilometers, you can actually perform particle analyses with a 5% statistical level within less than 1 week. And this is very, very powerful statement. This was our requirements that we wanted this to be achieved with a requirement of 1 month, but we see that most of it could already be achieved within less than that. So this was very good. In the end, the baseline solution became 100 kilometer, but of course now comes the next choice of, is this orbit at all stable? And this is what you see here. If you look at this particular table, this is what they designed. They looked at many different possible orbits. So you can see that the near rectilinear heliospheric orbit, which was tested with this reconnaissance mission, this lunar reconnaissance missions. Yes, they proved that it's possible, but it has a lot of issues with it. One being that you have to wait about half a year, well, not half a year, but 4 months before finally arriving to the moon. You might pass through the radiation belt many times. The electronics will be exposed. It can destroy. Then otherwise, once you arrive, it will be good. However, you're far from the lunar surface, so bad for science. So rejected from a scientific perspective. Now, then, if you go to 1,000 kilometers, you have different transfer types. You have the Hohmann like transfer, as well as the low energy transfer. we have two possibilities of arriving very soon, or it takes about 4 months. This was a reasonably acceptable, but it was difficult to keep the platform in its location because as it goes around the moon, because it's not as massive as the Earth, how to say, each impurity on the lunar surface, causes you to wiggle. So let's assume that you have a perfect sphere, then you make, of course, you orbit perfectly around it. But let's say you have a big crater and then a mountain and everything, then your orbit is actually wiggling. And then basically you are wiggling around the lunar surface. And this makes your orbit very unstable, and this makes it very predictable to understand what will happen if you do a 3-year mission, because you need to understand everything that happens, and every tiny thing will force you to make a correction. And if you need to make correction, you need fuel. If you need fuel, you need weight. You come back into this circle. Finally, we found an orbit, which is this eccentric, low altitude frozen orbits. It satisfies all our criteria as shown here. And this is in the end what the baseline orbits became for the Lumpan mission. Now, finally, we had the platform. We were working together with Aerospace Lab. This is a bit technical, so I'll go through it very quickly. They had a microsatellite ready to go, so they were reusing a lot of materials that they already flight tested. And ESA seemed to like the idea, and it was possible from a power perspective, from a data perspective, and from a mass perspective to actually launch it. So, and the criteria there was that ESA said it had to be within the budget of 50 million euros. And this is in the end what was possible. I mean, if you look at NASA missions, these are multi-billion dollar things. And ESA wanted to know, could something smaller and compact actually achieve it? And this is exactly what this group managed to do. Which brings us basically to where we are right now. So we have proven with this study that we can do a 3-year mission at the moon. So it is technically possible from a detection perspective, from a science case, it is very powerful, and from a financial perspective, it is very reasonable. We can do charged particles as well as neutrons and gammas as well as albedo inside the energy range that is of interest for the space physics community. We know that a baseline of 100 kilometer is possible, and we know that transmitting the data from deep space is possible at a reasonable cost if we use the Moonlight service. This is something that ESA is developing on. Now we submitted this to ESA. So this brings me to the last point. We submitted this to ESA. ESA said, yes, you are qualified to go to the next stage. But unfortunately, because of financial choices, one of the countries said, no, we don't want to pay for this big launch. So they said, okay, they said, you have to find a different launcher. And ESA therefore recommended us to go on this REMRED, this mission organized by REMRED. So this is a Hungarian institution that is pushing to actually launch something to space. So they have a national interest to go from their side. And so ESA said, yes, our science and platform case was so good that they said, okay, we still want you to go with them instead of what you had in mind initially. I mean, this is how it goes in the space business. You have one idea and they say, well, try with this. And right now we are beginning this stage to continue there. And we're now one step closer to the moon than we were last year, basically. And this is it.
Thank you
Thank you
very
for
much.
listening.
Thank you very much. That was a very nice talk. Uh, so if this RAMRED thing goes on, will you be launching, I don't know, is there kind of an estimate, maybe
I heard from them that they are targeting 2030 to 32.
32? Okay.
I am, I've been in this field for a bit long, so we will see, how geopolitical situations and everything happens, but um, uh, my estimate is closer to 2032. Yeah,
I see. All right. Thanks.
I mean,
I hope.
you know how projects go. When you have a very big project, it can a lot of things can happen, and this is one of them. This, okay, the mission target is 2030. They are being very aggressive at trying to launch it as soon as possible.
I see. All right. Thank you very much. So let me ask if there are any questions within the group of people we have. Uh, If not, I wanted to ask one more thing. So this, these detectors, they are working for secondary particles on ground, on Earth as well, right? I mean, there is no
Yeah, I mean,
issue.
you're talking about the time picks, the
Yeah, the
detector.
time peaks and everything, like detecting neutrons or like.
Yes, you can do that on ground as well. So I mean, I thought we are, how do you say? I mean, the collaboration responsible for it is called Medipix.
Uh-huh,
And in the end, it was designed as part of CERN. I think it was part of started and historically as part of the lab experiment at CERN, and then it evolved into becoming something that you can apply for medical applications. That's
I
why
see.
it's called Medipix. And
Uh-huh,
then at some point, the engineer said, let's have better timing in information, which is why you have Medipix and TimePix.
uh-huh.
And this TimePix is actively being used in the Atlas inner tracker because if you want to do the tracking of high energy particles and you want to know what happened at this interaction point, you need to be very close and you need to have very high rate. And at that point, of course, here they don't care about energy, how say, power consumption and things like that. But we, from space, we said, this is a nice technology. We can use it as well for space.
All
So
right.
it is a different way of going. It's a certain technology that we want to use for space. But of
Oh,
course, you have also space technology that goes back to ground,
sure.
depending on application. But in this case, we are trying to use CERN technology.
Oh, okay, cool. Thank you very much. I don't know if you can see, but there are two questions. One about the detection of neutrons and how it may affect the characterization of water on the moon. If I am not, yeah, I think that's it, right? Contribute to the characterization of water ice by measuring these neutron backscatterings. Is that
Okay, I just read it. Um, so to answer as far as I read regarding papers, the problem with neutron and ice is that, I mean, in general, is that you cannot go very deep underground in terms of depth. So if let's say I saw once a paper that was a guy about was trying to do this with glacier water. It was trying to understand how deep is the water on a mountain, and basically the ice in this case. And there, the finding was that if you go deeper than 5 meters, you don't know much. Now, the problem there was that we are like I mean, not thousands, we're like hundreds kilometers away at best. So, otherwise, we're further away. So, you cannot say, right there, we know at this depth, this is what is happening. What we can do is we can just do like a lot of orbits, and then after a while, we can say there's like over a big surface, like saying, you know, in this area around a surface of, let's say, 100 square kilometers, there is an increased concentration of hydrogen. I mean, this is what you can say. And then you think this could be water. And how deep it is, this is not something we can answer really. This is because we don't have what you call this telescopic effect. We are wide field of view. So if we had telescopic effect, then no, it would still not be possible because once the neutrons interact, they are destroyed. So because yeah, they are destroyed because they interact with the lithium-6 and then this produces the alphas. So you cannot do any directional analysis of it.
I see. All right. There's a
And
second question about the data transfer, I guess. You can see anyway.
Okay, how would data be translated in design requirements for lunar rover electronics, specifically in terms of shielding and components selection? Um, well, this is it's a very technical question. So we know what the problem there is not the GCR spectrum. So in this case, because there's no atmosphere, you know what comes from the top. So the
Yeah.
only problem is what comes from the bottom. And I recently was reviewing a paper on some shielding analysis from lunar habitats. Um, and in this case, the what you can do is by knowing the flux that you get from at our altitude, you can infer what the expected spectrum would be in reality on the lunar surface. So we cannot say on the first day, this is the spectrum, but we can say after multi-week, multi-month data acquisition, we can then say a story because then we've orbited multiple times. We have mapped the environments much more accurately, so we can now distinguish what is from space, what is from the moon. And once we know these two factors, we can actually combine them together by just superimposing, saying, okay, this is what you expect to see outside your window on the lunar surface. Then once you know what is outside your lunar surface, you just do a GM4 simulation and you just basically ask, okay, what do I see at the other side? And then the question is, okay, how much do you expect to see from neutrons? If you have neutrons, how do you shield against them? There was one paper suggesting to do like 2 meter thick. I forgot what it was, the material, but it was just way too much. Was completely unreasonable from a space perspective because you cannot transport concrete and things like that today, at least, to the lunar surface. So, but right now we are lacking actually shielding material that is low in weight but has a high Zeke property. You know, this sort of you're stuck with it a bit. But well, let's see how Elon Musk or will do with his goals. But
Uh,
this is now an engineering problem. This is not a scientific problem anymore.
on a related thing, so how long do you expect this mission to be around the moon once it reaches there?
3 years.
3 years continuous. Wow, okay, that's a
Yes.
quite long.
So our idea is to also monitor what is happening with the sun. So it is not just saying what is happening at the sun, but it's how does the sun impact the lunar surface. So really, what is the interaction together? And then we are bi-directional, so we can see really what is going in deep space and what is going on the lunar surface. And we want to have a big chunk of, well, I mean, it's 11 years, but we want to have a chunk of it of the solar cycle.
I see. All right. Okay. If there are no other questions, I couldn't see any. There's one, I guess, the wrong group. So, uh, are there any other questions that I cannot see? Please raise your hand or anything. If not, I would like to thank you very much, Johannes, one more time. It's a very interesting topic. I don't know if you were aware, but there is a Turkish mission to have a hard landing to the moon. Uh, Hopefully will happen sometime in the next few years, probably earlier than yours actually. We'll see. And there is a second in the at the moment being trying to be being planned actually, and they're looking for different ideas for like the idea is to put a rover on the moon and try to do some observations, experiments, and stuff. And so this was very interesting for us in that respect as well. Thank you very much.
This is actually quite interesting because we at ESA, I'm not fully wait, is Turkey part of ESA
No,
officially?
unfortunately not.
No, yeah, that's why. But we are in something called the Moon Pool as well. So
Uh-huh.
this is a pool of experiments that ESA selected, saying that, well, if we like you, we will put you on the lunar surface.
Oh,
So they said, okay, we like you, but we keep you in reserve. So we have been selected, but we are sitting in
in the
standby,
pool. Okay.
yeah, in the pool. Nobody has been selected. It's a typical ESA thing, but I will not say very more anything about that. But the thing is that that they have this concept of saying, oh, okay, we want to have some experiments on the rover, and they actually, I mean, right now, nobody is actively taking from the closets, all those experiments. And I
Yeah.
know from another colleague I once worked with, also in Prague, and also using the same technology as us.
Ah,
He is working on having the hard pigs, which is very similar like ours, but meant for just particle detection with Timex-3 technology.
mhm.
He wants to send this on a lunar rover. So it's the lunar rover produced by someone else,
I
and he
see.
has a simple device that is let me find something that's about this big. Yeah,
All right.
yeah,
Cool.
something like this. And well, actually a bit smaller than that. You just sticks it in as a USB drive, and then you just like, okay, and that's it. End of conversation. And then it does the similar concept like we are doing here, like this.
Uh-huh.
It has different shielding layers, and he only does it for charged particles. So he wants to figure out, do we have electrons, do we have protons,
I see.
things like that. So in our case, we are trying to do this with neutrons, and gammas, but he's only doing it with charged particles. So this is something, I mean, you can approach him if he might be interested in a collaboration.
All right. Well, there's one question. There's one more question, though. I guess it's not a big deal for you, though, because you will be very far away. It was about lunar dust, but I don't think. Did you ever thought
This is
about
not
that?
our problem. No.
All right. There's no wind, so
It's not our issue. We are not on the moon.
maybe for the rover it may be an
For the
issue.
rover with this other guy, this is for me. It's like I mean, our instrument is meant to be in space. It's really
Yeah.
meant to
Yeah.
be in space.
Hopefully.
It is really a, magnetic spectrometer, and the power of it is lost if you put it on the surface.
I see.
And so that's why we never pitched it to go on the rover. With the other guy who's doing this. I don't know how he does it. I would honestly think it would be a fun conversation to know how he solved this. But I mean, it might be. I mean, if I would make a guess, I would say that he would probably put like an aluminum shielding, like very
Ah,
thin,
yeah.
to protect it. Either that or just MLI. But I think he would do something like that to protect it from any stones and particles like that. And the dust itself doesn't really matter because it you can see in the spectrum if there is, for example, some particular mineral that is interfering. You
Yeah.
would notice that the spectrum suddenly changes, and this is enough for them because they are just doing the same trick. They're just monitoring.
Yeah.
So suddenly, if your spectrum monitoring puff changes, then there's something. And well, okay, I
I
don't
see.
know how to clean that. Maybe they have compressed, so they don't have air. The compressed, well, they need to have a shaker then. I think they need to have some sort of
I don't
shaker.
know. Okay, thank you very much one more time for this talk. It was very interesting, and hoping to meet you sometime in person or anything. Right. Thanks a lot.
Yes, likewise.
Bye.